Hello, my name is Hoai Bengtsson from Volvo Car. I'm going to present the topic about the holistic analysis of task scheduling and message scheduling in the automotive centralized EE architecture. So co-author of this work, we have two more co-authors, Martin Hiller and Fredrik Masson from our system architecture team at Volvo Car, and we have one colleague from SAP, based Sweden, Bengtsson. So this is a continuation work from last year. So last year at the Automotive Technology Day in Detroit, we have presented challenges when moving from the domain architecture to centralized architecture. We have addressed number of challenges. Moving from domain architecture to centralized architecture, meaning that we will have a vehicle central unit to do all the computation. We have a vehicle integration unit placed in different positions in the car. In our case, we have a front, we have a left, and we have a VIU in the right. We have a number of nodes connected to the system, either with a CAN bus or with the Ethernet bus. But we have on the Ethernet backbone. So the challenges was we have a lot of applications running in the system, meaning that more amount of traffic sent over the network with different timing requirements. So how can we guarantee that those timing requirements are fulfilled? We also have a lot of ECU that's been using CAN bus. So we have to do some kind of gateway function in the vehicle integration unit. So making this, how to use it in efficient way is also another challenge. So if some of you might recall that we have presented it, how we solve it. But we only focus on the network part. So what's the lesson learned from that last year, from the previous work? So we have a proposed to you number of the TSN feature in the ASIO 2.1 standard. For example, we use ASIO 2.1 AS or synchronization. We use ASIO 2.1 AT for the stream preservation, and then we use some credit-based shaper. So using those features could help us to provide the bounded, but it's only for the network delay. So what's left? On the right-hand side, you see how the system look like. The device, here's the number of the ECU. It can connect to vehicle integration units via the CAN bus, or some of them can connect directly via Ethernet. And the VIU will connect to the core, the vehicle central unit via the Ethernet. Here's a 1 gigabit link. So when the frame is sending via this Ethernet link to the core network, we will have something called the device proxy. So device procedure is that it will extract the frame to the signal. So in this information, you can see, okay, which function are gonna be run on the system. So it will keep running one function, and then when the function is complete, it will send out the result to the device proxy again. Then device proxy then will send out the result via the Ethernet link, via VIU, and go to the actuator. So that's complete will be from the sensor to VIU to the core system, running some task, send out the result on the sensor. As you see, so the performance of the centralized processing function largely impact the sense and the act response time in the system. So the response time analysis of the response time of any message will depend on multiple factors. It will depend on the network delay when you send the communication over the network, processing delay at the end node, processing delay inside the core system, and the scheduling mechanism, especially when with the centralized architecture, you will have many functions running on the core system. How you schedule those functions will have a greatly impact on the performance of the system. So therefore, In order to verify our system design solution, we continue the previous work with this added the simulation tool to do the processor scheduling to integrate with the previous network simulators. So this tool allows us to provide the end-to-end delay analysis, including the network delay and the task response time inside the processor. Based on the result, we can suggest the strategy, scheduling strategy. By choosing the suitable scheduling strategy, we can increase the predictability of the system as well as to warranty the real-time performance for many applications. So, our design approach. Automotive is moving towards a software company, as we all know. The system is abstraction as a number of the function with a lot of requirements. By choosing certain hardware platform, how can we deploy those functions in the platform in such a way that all the requirements are fulfilled? So we need to have a group, which is a system design, where we are belong to. So we have done some work on the communication protocol and network scheduling on how the communication in the platform. So what we lack is we need to have somehow some method, some tool to verify how we allocate resource to different tasks or different applications in the system. So altogether, this is the focus of our talk today. It's about holistic analysis of the system, where we have a resource allocation, process scheduling, and the communication scheduling. So in this slide, I want to recall about the previous work on the network scheduling part. So in order to support quality of service for the network traffic in the system, we divide whenever the traffic arrives to the system. It will be divided into different queuing at the ingress port of the switch. In this case, we have a two switch block A and switch block B. And then for the control traffic, we use UDP protocol and put it in the highest priority. So we can pre-calculate in advance in such a way that the control traffic doesn't take more than 25% of the load. And then we use priority 5 for the audio traffic class A, priority 6 for the video traffic class B, and we use credible shaper for the AVB traffic. So for the software download and diagnostic, we use the best efforts traffic. We have a lowest priority, in this case priority 1. So in this way, we can provide some kind of bounded delay and the bandwidth reservation for different traffic class in the network. Okay, moving to the processor part. We need to do resource allocation and process scheduling. So what are the new challenges then? Again, our central compute unit VCU must handle much higher workload compared with the domain architecture. And then some of the applications, many of the applications are implemented in the VCU, and some of the applications are implemented at the end node. And then they have a different timing constraint. So how can we do scheduling inside the VCU in such a way that those timing constraints are met? So there are different factors that affect this. The most important factor is the choice of scheduling policy, especially if we want to know how the system behavior. We have to choose the correct scheduling approach. And also scheduling approach can help the system designer to determine whether the system is work behavior as it is expected when it's overload or prevent overload situation. So talking about the scheduling, traditional in the real-time operating system or real-time system, we have a dynamic scheduling and static scheduling. In this case, I'm talking about the dynamic priority and static priority. So traditionally in automotive, we only use static priority. So in static scheduling approach, because most of the applications requirements are known in advance, so that we can do the scalability analysis, meaning that we can bring the feasible system at the design stage. But now, when a lot of new applications will have there is a need for dynamic scheduling as well. But however, in this work, we only apply the static priority with, especially for the safety critical system. Another thing that should be considered when building the system is periodic system versus sporadic system. So again, in the automotive, everything about time-based. When we're building the system, everyone say that, okay, we have a periodic, we send everything periodically. We have a periodic system, so that's allow us to increase the predictability. So the period of the event is a minimum arrival time. But many applications, especially in the new generation vehicle, many new applications that's based on the event. In the domain architecture, maybe periodic, we can handle the system with a periodic arrival of the event. But in the centralized, using the periodic, building the periodic approach will soon lead to the overload of the system. So we defined, in this work, we define the periodic task. The tasks are really by the periodic event, and those are activated based on the system clock regularly. And we have a sporadic task, other tasks that are released by the sporadic event, also tasks with the stochastic computation interval. Those are activated whenever the event related to the task happen. So both of those have a pros and cons, as I said. Periodic system known for its predictability, but is a waste of utilization. Again, the sporadic system, we can maximize the utilization. We can have a shorter response time, but again, it's difficult to predict in the worst case scenario. So therefore, we are thinking of building a combining approach. So when we're modeling the system, we're modeling the processor or software system inside the VCU. So system will consist of the sets of periodic tasks. Each task is represented by 3 parameters: the execution time, the period, and also the arrival time. But in this case, we analyze the worst case when everyone arrives at the time 0. So it is known as the worst case situation. And we assume that those periodic tasks will not use more than 50% of the system utilization. The reason is that we want to reserve the resource for the periodic task. So another part of this system is a set of the periodic or sporadic task that associate with the sporadic event. Those have arrival time and execution time only. Now, we make some assumption before we do any evaluation. We assume that all tasks are independent. So there's no dependency between the tasks in the system. So each task in the system is assigned a unique priority. Even if it's sporadic or periodic task, they have 1 priority each. And as I said before, periodic task is activated by the system clock. Sporadic task is activated when the event occurs. And we allow to have a preemptible or preemptive scheduling, meaning that whenever the task is activation, it will put in the ready queue. scheduler in the event take the first one in the ready queue, putting it on the running. The ready queue is sorted based on the priority, and when the higher priority task arrive, it will preempt the lower priority task and put back to the ready queue. We have some tasks that in the waiting state where it waits for the external event to occur. The interesting thing with scheduling an event-based system is that when we look at the PO6 standard, there is a sporadic scheduling approach, which based on the sporadic server approach, which make the sporadic task behave as periodic by assign replenish interval for the sporadic task which act as a period, so that we can analyze the system so we don't lose the predictability of the system. Now, in the next slide, I will explain to you how this sporadic scheduling works. Now, assume that you want to schedule a sporadic event. So first, we assign two new parameters for this event. One called the budget, meaning that how much it can be executed during the certain period called the replenish period. In this case, this event can be executed maximum 8 units during the 12 unit. So let's say when the event occurs, the task is executed until 4 time unit, then there is a higher priority task arrive. Because we already use 4 time units, we subtract 4 from the budget. And then something happened, it had to wait. At the same time we executed this task, we start the first replenish period. So now, okay, we know that it has been only use 4 during the period of 12, and it allows you 8. So if this task is activated again, let's say at time 6, and then executed 3 more units, so we subtract 3 from the budget, and also we start the second replenish period. And then we check if the processor is idle again, it will be executed again, and then when until it's complete. So this task have an execution time of 10. And then again, we restart the third replenish period. So by this way, you see the sporadic event act exactly as a periodic task, so that we can do the theoretical analysis, and we can also calculate the system utilization based on those parameters. With that said, we apply sporadic scheduling approach for the sporadic task, and then we use priority scheduling for the periodic task. I will explain in detail how we build the scheduler or how we modeling a single core processor in a VCU. So when we have any time we have a message arrive, we buffer it at the hardware interface. At the same time, we generate an event. So we put those events in a queue. So we have one event queue. We preloading on the parameter of the periodic task set in the memory. So they are preloaded. Also on the sporadic task, also preload. The only thing that we don't know is that when those one will be executed. And those periodic sets are activated based on the system clock. So what the scheduler does is that when it look at the event, okay, extract from the frame here to the signal and look at the signal to see, okay, which task is related to this event E1. Let's say it's the S1, task S1. It will take task S1, put in the ready queue. Now this ready queue is sorted based on the priority. Let's say there are already 2 tasks, periodic tasks are running, waiting in the ready queue. If S1 has a higher priority, it will put it first in the queue and then running, and then put it out to running. So this is how, that's why we have one unique priority for each task, either sporadic task or periodic task. They are not the same queue. So we put in the running. What the scheduler do is that every tick or every system tick, it will check, okay, is there anything coming yet? Is there any event? Is there anything that should be activated? And checking a ready queue to see, okay, which one is running. And at the end, when at the output, send out the output, then we can measure the time it takes in the processor to handle this event. Okay, so we, in order to evaluate our approach, we do the simulation. So we do a very, very simple scenario. We have the vehicle computation unit with two switch block, the inside two switch inside each block. And then we have one processor with single core. We have a 3 vehicle integration unit, the right, the front, and the left. And each of the VIU, we have a 2 client connected to the VIU. We have one client is sensor and the other one is the actuators. The connection from VIU from the end node to the VIU is 100 megabit. And the connection between the VIU and the switch in the core system is 1 gigabit. So here. So we first, when the event happen or when the message arrive from this sensor, it will send all the way via the switch and go to the processor. Since that we can measure, we measure all of this time it takes from sensor on the network scheduling part, and then we can measure the time it takes until this message arrives to the processor. And then we do some scheduling. We do the scheduler task. Scheduler, what it does here is that it's running the task, as I explained before, send out the data, and then we can measure the time from when it's arrived, the message arrived, running the task, and send out until it's arrived to the actuators. So by this way, we could measure the end-to-end response time. So that is a simulator. Some of you might saw that before. Here, so we sorted the traffic in different queues, as I explained in the communication scheduling. And then I can have a core simulator written in Java. Every tick I check what exactly happened in the network and what exactly happened in the processor. So the new part of this time is that how can we handle compute in the processor. So the reason is sent out to the MATLAB, then we can plot the curve, we can measure the maximum and the minimum delay. Now to start with, we start with very simple scenario with 6 periodic stream as defined here. I use a DSN parameter, which is 256 microseconds, with the payload is 1171 bytes. This one have a 512, and then we have also with some stream, 2 stream with a period of 1 millisecond. And then we have a 4 sporadic stream. Here you see, from 7 to 10. This is how I define the stream. Now you see so I already defined on the stream on the system, and now I define the task set. We start with very simple task set so that we can verify the simulation work correctly. So for the priority task, here we have only 3 priority tasks. So we set the priority for them. So we have a priority 11, 9, and 7. And then we have a period for the priority task. And then we also have an execution time. And we have 2 sporadic tasks. For the sporadic task, because we apply this sporadic scheduling approach, we need to have a priority normal, and then we need to have a priority low, meaning that during the replenish period, sporadic task is executed during its priority normal. Until the budget finish, it will automatically switch to priority low. So we have a budget, we have an execution time, and then we have a replenish period for the sporadic task. Now come to the simulation result. So what interesting here is that without the processor scheduling, you see here is the stream one, the upstream one from the sensor to the processor. You have a very short delay, 58 microseconds. But of course, in this one, I assume that the system are perfect synchronized and no scheduling overhead and no jitters. So therefore, you see a very nice number. So it's a 58 microsecond. Okay, now round trip without the processor scheduling. The round trip should be double this number, so like 120 microsecond. But now just add one processor with very few tasks, only 5 tasks. You already see the difference here. Some frames have a latency of like 180. Some of them have a 270, and some of them have almost 400 microseconds of delay. Why it look like this? First of all, because the system is perfect synchronized, no jitter. So the one that missed the period, the task period, it had to wait until the next period when the task is executed. So therefore, the delay here is one task period. And then some of them miss the second one, so it will be executed until the second period. So you see, they miss 2 periods. So that is what happens when you have a scheduling inside the system as well. Here is for the stream 3. And then here you see how the uplink delay without the processor. And here you see how when you add the processor, delay into the number, the reason. Now it's more interesting. We see stream number 7 is a sporadic stream with a sporadic task. So you see here it's a very unpredictable because the event arrive according to the Poisson distribution. So you see the distribution of the delay are completely different. Many of them have a delay about 800 microseconds, and many of them have a delay about 300 microseconds. So those are very small scenario just to show you that how the processor scheduling affect the complete end-to-end delay of the message in the network. Okay, so that's come to an end of my presentation. So in summary, we have present a holistic approach for modeling analysis of the network processor and performance in automotive systems. So we have integrated the network scheduling with the processor scheduling. So we see that the processor scheduling have a great impact on the end-to-end latency of any event through the system. So the tool is more similar to pre-study. So it allows the designer to calculate or to estimate time of the sporadic and periodic event. And based on that, we can have a suggest the right direction, which scheduling we are going to use in the system. So there are a couple of things we could do as the future work. We could extend the processor model to capture multi-core scheduling. We could add some changing the clock resolution in the system. Now we have only 1 microsecond, but we could changing that number. We can also add some jitters in the system as well. So thank you for the attention. Any questions?